Visual Studio Debugger. I've been working on the debugger for nearly 20 years now. Usually the program managers do these talks, but this time they let me come and do it. So this talk is going to be about some of the lesser known features of Visual Studio that can be really powerful for your debugging techniques, and I'm going to move through some of the newer, more advanced features we've added in 2017 and some of the cloud-focused features that have been added during the VS 2017 timeframe. So the first thing is, let's see if my IDE comes up. I don't really have any slides. This is going to be very demo focused. There are slides that cover some of this that I put up on the website, but I'm going to stay mostly in the IDE and not show the slides. So this is a project that we use for demos. It's a pretty simple recipe app that has a couple of different projects in the solution, and it's just a little database that lets you look at some different recipes and search for some of them. So I'm going to go ahead and hit F5, which starts the debugger, and let the app start. And in the meantime, well, there we go, it came up. So it just has some recipes that come up, and I can search for something like beets, and it turns out I don't have any recipes that use beets. So going back to the IDE, this solution actually has two projects in it. It has a service and a WebMVC app. And so the first thing I wanted to show is that the Visual Studio IDE and its debugger can actually start multiple projects simultaneously when you start debugging. And it can optionally debug multiple projects or just one project at a time. So if I want to switch to launch both of these projects, I can change this to multiple startup projects and set these both to start. And then when I start debugging either through F5 or through one of the other techniques, it'll actually launch both of these processes under the debugger, and you can debug them simultaneously. I'm not actually going to do that today for the demo, though. I'm going to stay in a single process. The next thing is that if you want to debug the startup code for your application and you don't necessarily want to go find it or you don't know where it is, the debugger can actually start and break right at the entry point of the application automatically for you. And so that's pretty simple. It's just a step in or a step over when you're sitting in design mode, which is F10 or F11. And the app will actually start up and stop right there at the entry point. So this can be convenient if you don't know where the startup is or don't want to have to go find it or whatever. Go ahead and let it run. All right, so the next feature I want to show is something called run to cursor. And this is a way that you can move forward in the application over a chunk of code without having to go set a breakpoint or remove the breakpoint when you're done. It's like a temporary breakpoint that we set just for the duration of that operation. So once the app comes back up, I can search again. And when I hit this breakpoint, I can select a line of code that I want to run to and choose run to cursor. Or you can use this new glyph we have that shows up here on the side of the code when your cursor's over it. This is called run to click, and if you click on it, the debugger will run to that location. Another thing you can do is if you need to go back and the code that you're going back to doesn't have side effects that can need to be undone, you can use what we call set next statement. And this is a hard set. This isn't a reversible debugger. It just sets the next instruction back to that location. That's also available here in the menu under set next statement. Or you can bring up that glyph again under the cursor, hold the control key, and the glyph changes to that little arrow, and if you click on that, it'll set it back. And then the app can continue to run. So another really powerful feature we have that's not really well known is something we call step into specific. And this is useful when you have a line of code that has several functions on the line and you don't want to be stepping in and out of each of them over and over and over again. It's fairly inconvenient. So instead, what you can do is using the step into specific, you can choose a specific function that you want to step into. So sitting at this breakpoint here, if I were to step in, it's going to go first into response.data, then into getRandom, then into the title property, then to toUpper, then get fancy name. But let's assume we just want to go directly into getRandom. So if I right mouse click again, bring up the dialog and choose the step into specific option, it has a list of all the functions on this source line. I'm going to choose getRandom, select it, and it'll take me into that function and stop. The next feature I'd like to show is something we call trace points, which is the ability to add trace statements to your application while you're debugging them dynamically. Trace points are kind of like breakpoints, except instead of stopping, they just print data to the output window. There's an entire language that can sit behind a trace point that you can use to control what you actually want to be displayed. So to set a trace point, you set a breakpoint, right mouse click on the glyph in the gutter, choose actions, and then type what you want in here. And so the first thing I'm going to type is just trace point, and that's because I have a lot of things coming through the output window right now, just to make it easy to find. Then I'm going to use something called a pseudo variable, and a pseudo variable is variables that are built in the debugger that can show you state about your application that's not available in other ways. So for instance, I can have it automatically print the name of the current function, or the address of the current IP, or there's a whole set of these that you can see under on the IntelliTrace menu here. But the trace points also allow you to evaluate state in your app. So if I want to see the response, like the value of a property in the response object, can put the response object, the evaluation I want to do inside of the bracket, and say that I want to evaluate if it was successful. And so by putting it in the bracket, that tells the debugger to go ahead and evaluate this. And go ahead and hit enter. And now when this code executes, we're going to see that come up in the output window of the debugger. So having that code run, I switch the output window. Try that one more time. Sorry, what? It's, oh, it's not continued. It wasn't continued. It was sitting on the stop button was visible, so it was in run mode. But we'll restart it and have it go again. Okay. So here's an example of my trace point that I've highlighted right there. So it says that it's a trace point because I made it say that. Here's the name of the function, which includes the types of the parameters, and then that the success was true. So this was the variable that evaluated in that property getter. So this can be very powerful if you have something that that's going to execute a lot and you don't want to be stopping on them, like if you're looking at a ref count issue or a code path that's very hot. This can be a good way to narrow down the root cause of an issue without having to hit a breakpoint and constantly restart each time. So the next thing I'd like to show is some inspection tips, and these are some things in the watch windows that you may not actually be aware of that are very powerful. So going back to the app and running this location, the first thing I want to point out is that evaluations in the debugger typically, if they have side effects, those side effects are flushed to your app and they actually occur. So if I evaluate the variable index and then I evaluate that again with index plus plus, the plus plus operation is actually going to get written back to the debuggy. You can see that the value of index actually went up by 1. We do have another concept in the debugger called a format specifier, and that can control both the way that a variable is viewed. You can change the format to, say, hexadecimal, for instance, or things like that, or you can actually use it to change the behavior of the debugger when you evaluate a certain expression. So in this case, I'm going to evaluate the no side effects expression, or format specifier. And what this tells the debugger is do not flush this value back to the debuggy. So the next time I come around, if I evaluate this again, the plus plus actually occurred, but it didn't write it back to the actual debuggy. So the real value of index stays the same. If I step over that, because that plus plus has a side effect, it's not going to evaluate it a second time. So if you look at that in the watch window, it's gray. In order to evaluate that a second time, even though I know I said it has no side effects, let me take the no side effects back off and do that one more time. So the debugger is smart enough to know that that variable actually had, that evaluation had side effects. And it's not going to evaluate it a second time when I break. So see how it's all grayed out. You can force it, though, to actually evaluate it every time. And you can either force it by clicking on the refresh button, which will make it occur and write back, or you can put a format specifier on there that says to always evaluate it. And that format specifier is AC, which stands for always call. And that's because it's normally used in the context of a function evaluation, which is how we evaluate properties. They're actually executed in the process. And generally, the func evals can either be virtually evaluated or are evaluated for real, and so that's where the always call name for that comes from. So The next thing I'd like to show is something called the ability to visualize return values in the debugger. And that's for scenarios like this where you have a line that has multiple function calls that all return values that you may not actually see. So if I hit this breakpoint and step over, if I want to know what the to lower call returned or the to upper call, it's not really visible. The first place you can see it is in the locals and autos window. It'll actually show you each of these functions and what they returned. So to lower converted that original string to all lowercase, then to upper converted it to uppercase, and trim took the space off the front. You can also access that using a pseudo variable, which is $return value. If you don't put anything on the end of it, if you just put $return value, that'll give you the return value for the last function call that was made. But you can also force it to show you previous return values from that line by putting an integer index on the back of it. So $return value 1 gives me the to lower call, $return value 2 gives me the to upper call, and then return value 3 will give me the call to trim. All right. The next thing I'd like to show is one feature that people really like in the debugger once they found out about it, and that's something called debugger display attribute. So normally what the debugger does when it sees an object is it calls the toString method of that object, and it displays that in the default view. Well, the toString method for most classes, if you haven't overridden it, just shows you the type. And the toString method can also be used by your application, so you may not want to modify that in order to control what the debugger shows. Instead, we can use the debugger display attribute to control what the debugger actually shows. So if I have that class recipe that I was just showing in the debugger there, and I add an attribute to it that contains a string, I can control that default display. And it uses the same syntax as trace points. So I've put the title property in here inside a bracket so that it'll execute that. And I've also put the ID property. And I've added 2 format specifiers. The first is NQ, which is no quotes. The second is H, which means show this in hexadecimal. So now if I start debugging the app again, hit that same breakpoint that I was at before. If I view that recipe collection and open up the collection, now it's showed me the view that I wanted to see of my object automatically. So here's the name of the property that I evaluated, which was I believe was called title, and the ID, and that's in hexadecimal. Another really powerful, underutilized tool in the debugger is something called an object ID. And what this is you can create a identifier that holds a weak handle to an instance of an object that you can use to reference that object, even if it's not in scope. So this is just a simple little app I wrote to demonstrate this concept, where I've created 1,000 instances of this object called squid. And I've set a conditional breakpoint on that to show me the 6th squid when it's created. So if I go into the watch window and type S, it'll show me that object, squid. But if I hit continue here, the squid's going to go in the collection, and then it's going to be really hard for me to find it. I'm going to have to go through the collection and look for it. And it may, if it goes out of scope, I won't even be able to see it. It could be sitting in some global collection or whatever. So what you can do is right-mouse click in the watch window on that object and choose Make Object ID. And you see that the watch window added this $1 at the end. That's a weak reference to that object. So any place that I could type S, I can now type $1. And that will bring me back to that same instance of the object regardless of where I am. And one of the cool things you can do with this is you can use it for, say, conditional breakpoints. So later on in this loop, this app is going to modify the size property of all the squids. And let's say that I only want to see break when the size property changes for that instance that I made the object ID for. So if I add a breakpoint to the size property of the squid, right mouse click and choose conditions, I can say that I only want to break if this reference to that object equals $1. Hit enter, run F5. And now, when it breaks, I'm sitting at that conditional breakpoint only for that instance, for the 6th instance that was in that collection. And just taking a value, or looking at it in the debugger, you can see it does have the $1 tag on it, and so we actually are at that location. All right, another thing that I'd like to show is something new we added maybe a year or so ago. It's called a perf tip. And the perf tip allows you to see the runtime cost of an operation in the debugger without having to add any instrumentation or fire up a profiler. This is a wall clock time that has a lot of smarts behind it because it has to remove the overhead that the debugger injects into the process. So say that I want to know exactly how long this REST API, this async task that calls a REST API takes. Starting the app back up, I'm switched back to the recipe apps, by the way. I'm off of that other demo. But running the app again, when it starts to populate that recipe app, I'm going to stop at the breakpoint before the call is made, and I'm going to hit F5. The debugger started a timer, and when it's ended, it says that it took 444 milliseconds. And that's 444 milliseconds wall clock time with the debugger overhead removed. So it's actually integrated in with the kernel, and it knows when there's context switches occurring because the debugger is adding all kinds of context switches and stuff to the app. It actually works when you're stepping as well because of those hooks, which adds significantly more context switches than what I just did here with that little run. How many of you all have used IntelliTrace? Are you familiar with IntelliTrace at all? So in the latest release of IntelliTrace, we've enhanced it with something we call process snapshotting. And a process snapshot is a very efficient in-memory copy of your process that shares the same memory pages with the original app. They're very fast to create, and they let us point the debugger at that app and see the state of your app at an earlier time. So pull those up really quick. Start the app one more time. So let's say that I've set a breakpoint at this location and I ran forward to this other location here. In the IntelliTrace window, which is under the diagnostic tools, under the events view, I can see that I had this previous breakpoint that I was sitting at, and it has a camera icon next to it. The camera icon means that that event is backed by a snapshot. So if I click on that and activate historical debugging, the debugger will take you back to that location, and it has the entire state of the process at that point available to it. The previous releases of IntelliTrace, it would be limited only to what was visible in the watch window when you stopped. So I can see the entire call stack, and I can evaluate every variable in the heap at that point. So I can drill into the response object, and I can look at all of its properties. I can look at its strings, its content, and stuff like that. This also works in 15.9 with exceptions. So if an exception was thrown that you didn't stop on, the debugger will automatically create a snapshot at that location, and you can go back in time and look at that exception and view the state of the application at that point as well. So it works in both scenarios. The same technology, the snapshotting technology that we've integrated here into F5 is also available for cloud debugging, and it's a new type of debugger we call the snapshot debugger. Essentially what it does is instead of creating the snapshots on your development machine while you're sitting in different break states, it pushes the information about where you want snapshots to go up to the server. And the server is running a fully retail optimized build. We didn't force you to put a debug build or anything up like that. And when the breakpoint, that snap point is hit, instead of stopping the process and making it so that your user can no longer interact with the app, instead it creates a process snapshot and we can point the debugger at it. So this allows you to debug what's actually happening on your live server without impacting the users that are actually using it. I'm going to demo this, and this is against real Azure, so assuming there's no network issues or anything like that over the Wi-Fi, I'll start it up. There's a little bit. There's more once you actually attach to the process, but the compute cost is very small. It instruments the application to inject p-invokes that actually make the calls to the snapshotting API. And then it also interacts with the JIT compiler to ask it to remove optimizations that make that function undebuggable for the duration of it. So normally, if you were to attach the normal managed debugger to that process in production and hit a managed breakpoint on a retail build, you're not going to see anything. And that's because the JIT compiler optimized the code and it removed something called sequence points from that function. So we asked the JIT compiler to recompile it with those optimizations disabled for the duration of the breakpoint, and we put the sequence points in place. And then once the breakpoints hit, we rejet it back to fully optimized. All right, I've got the snapshot debugger started against real Azure. I can come in here and set a production breakpoint on this line here. And you can see the breakpoint, not a production breakpoint, I'm sorry, it's a snap point. Production breakpoint was an old name for it. Set the snap point on this location, and you can see it's purple. It's not the normal color of a breakpoint. You can also see that it hasn't bound yet. And the reason for that is if you want to push multiple snap points up simultaneously, we want to do that atomically. So you actually have to push a button that says, update these against the server. So I'm going to go ahead and click that button that says I want to update them. It's going to push it up to my live server, and now it's filled in and bound. It looks just like a normal breakpoint in the debugger. If I come in here, right mouse click on my app service, and say that I want to view it in the browser, it'll come up running on real Azure, and you notice the breakpoint turned green. And there's a new event in the IntelliTrace window that says that a snapshot was taken. The snapshot's sitting on the server, but as a user, I can sit here and fully interact with this. There is almost no noticeable difference in terms of the performance of the application. And we have some good performance analysis of this available on the internet, on the blog post that introduced this technology. So sit here and interact with the app, and it's running great. Okay, now the developer comes by and wants to actually see what's going on. So I can click on the snapshot and click View Snapshot. Now it's going to launch the remote debugger on that app service, because this was an app service application, and it's going to attach it to that snapshot instead. So while that happens, just sit here and continue to play with it. It's still responding. There's nothing as a user that makes me aware of the fact that I'm being debugged, or the application that I'm using is being debugged. And once the remote debugger actually comes up, the call stack will be visible, and I'll be able to view the entire heap at that location. Other features of snap points, while this comes up, are you can set conditions on them, and those conditions use the same syntax that the regular conditional breakpoints in the debugger use, but the conditions are evaluated virtually. They don't actually execute in your process because we don't want any side effects against a production process. And you can also dynamically inject trace statements using this. So if you have a live site issue and you need to add some tracing logic that wasn't there, you don't necessarily have to redeploy. You can use this with the same trace point technology I showed earlier to create a dynamic trace statement and add that to your application. And that's the variables and things that are evaluated in your trace statement are also evaluated virtually against the process. Come on, you can do it. All right. Well, that connects really quick. I'm going to ask, does anyone in here write any C++ code? Are there any C++ devs? All right, there's a few. Awesome. We have some cool new features in C++. I'm happy to announce that C++ actually supports the same snapshotting features that C# does. Oh, it hit. So I'll go back to that in just a second. So here's the call stack, and I can evaluate my variable. And this is evaluating it against the live server. And the reason that says the debugger is unable to evaluate the expression is there's a debugger display attribute on that can't be executed right now. And like I said, this is running against real Azure. It's in the West US data center, so it is remote debugging across the cloud here. And over Wi-Fi on a loaded Wi-Fi system. But there, yes, okay. The entire managed heap, yay! All right, so it's enough with the snapshot in C and C#. I'm going to switch to a C++ application. And the first thing I'd like to show is some lesser known features of the C++ debugger. So if you've ever written C++, especially against Win32, it's an API set that's not super easy to debug. A lot of things are integer values. When failures occur, the functions don't tell you what failed. They just give you an error code, and then you have to ask for the last error using getLastError, which gives you an integer value, and then you have to convert that integer value to a string in order to get something user readable. Well, the debugger can do all of that for you. So I just have a little Win32 C++ app here that I'm going to break on. And if I want to, say, take a look at a Windows message, which is a numerical value that the debugger doesn't understand, or that is difficult to understand because you don't have any context of what that actually means, the debugger does know what that is, at least for the well-known Windows messages. So if I type message and use a format specifier, which is WM for Windows message, it's going to go and look that up and say, oh, look, that's a WM command. Another really cool feature of the C++ debugger is the ability to get the last error and format it for you. So I've got these two calls to get environment variables that have bad environment variable names here. And if I need to see why that failed, I can type the a pseudo variable for getting the last error, which is $error. And you see that the last error code that would have been returned if I had asked for last error was code 203. But what does that mean? It's just a numerical error that doesn't mean anything. You can also get the debugger to format that automatically using the format specifier HR, which stands for H results, but it works for both Win32 error codes and for H results in COM. And it'll go look it up and say that, hey, that was an environment variable that wasn't found. One of the cool new features we've added in this release is an easier way to get to data breakpoints, which are, data breakpoints are a way for the C++ developer to break when the value changes. So you don't have to continuously hit a breakpoint looking for where it changes. You can just have the debugger tell you. Previously, this was hidden under a menu in the breakpoint window. You'd have to choose data breakpoint and type ampersand and the expression you were interested in. And it was a fairly clumsy way to get access to that functionality. Well, now, with the latest release, I can just select an expression. Let's say I want to know when the verb field of this struct changes. I can add it to the watch window. And then I can right mouse click on it and say break when the value changes. And the debugger will automatically do all of that. And it shows you what the original expression was as well as what the address is. And if I continue, it'll break at that location. And I can see that, yes, in fact, the LP verb was just changed. And the reason that the line is on the next line is that the way the hardware that supports this works is it's after the instruction executed, and then the current instruction that's about to execute is on the next line. Okay, and like I alluded to before, the C++ devs are not left behind when it comes to snapshotting. So if I go into the diagnostic tools window, I can see that I did actually hit a breakpoint here, and it has a camera icon next to it. If I step a few times, as I step, my steps are also getting the breakpoint icon, or the camera icon on them, and I can choose a previous location, activate historical debugging, and it'll take me back. And I can see, once again, the entire state of the app at that location. All right, one more cool thing I'm going to show for the managed developers is some memory tools that a lot of people may not know about. And going back to this little toy application that I had this squid list that had 1,000 of these squid instances in it. So let's assume that I need to take a look at the managed heap and somebody's creating too many squids, but I don't know why, and I don't know what's keeping them alive. So going back to the diagnostic tools window, if I hit a breakpoint, I can go to the memory usage window in this window here, and I can tell that I want to take a snapshot. And this is a little poorly named because it's a different snapshot than the other snapshots. But this means that I want to take a view of the managed heap at that location so I can go back and inspect it later. Then if I step a few times, I can do it again. So what this is actually telling me is that the managed heap has 1,209 objects on it. It's currently consuming 94K, so not a whole lot, but you can imagine that a code like this could consume a lot of memory. But let's say that I need to drill into these objects and see why am I consuming so much memory. If I click on this, it'll actually pull up a view of all the number of instances of each type in the app. So you can see that there's 1,000 instances of squid that have been created in this application, and it's 24K that's being consumed by that. Okay, that's great. What's holding these squids open? So if I click on those squids, it'll pull up each and every instance of them. And from that, I can drill into what's holding those objects open. So this one, for instance, I can see the instance of squid is being held by an instance of list. And if you go back to the source code, of course, I had created 1,000 squids in that list. Squid itself is a local variable, which means that it's not truly a memory leak, because when this function exits, that local variable will become eligible for garbage collection, and when it's garbage collected, then its contents will be garbage collected. So in this case, as long as this function exits at some point, it's not actually a true memory leak. But you can imagine where this could be very powerful if you had a collection that was constantly growing, or a cache that you were never clearing. You can pretty easily dive into why that sort of thing is actually happening in the IDE. And then one more feature I'll show, because we actually have a little bit more time, is another one of our performance tools in the debugger. So if I start debugging again, back to the recipe app here running locally, and switch back to the diagnostics tool window, I can go to, say, CPU usage, and I can actually take a CPU trace of my application while I'm debugging it. So I'm going to go ahead and enable CPU profiling here, and I'm going to run from, let's go ahead and just let it run for a little while. Hit F5, let it run. All right, once we're finished with the scenario that we're interested in taking a look at the performance of, I can hit break. The debugger will stop, and it's going to process the data to give us the trace of the call stacks where the performance was actually being impacted. So this is our normal performance profiler UI here in the Diagnostic Hub. But I can see that 1.12% of my time was being spent in get all recipes. I can click on that, and it'll take me to, oh, it should be taking me to source here, and it's not. Okay, well, I guess that one's not going to work, but it would have taken me to source on that location. At any rate, that's the duration of my talk. I don't have anything else to share, except for that I have some links to some of the documentation for some of the features I showed today, which will actually be on this machine. So the features that I showed you today, the format specifiers are documented on MSDN. There's a couple of different pages you can view for that. The pseudo variables are documented here. Debugger display attribute is documented here, and you can point back to format specifiers and trace points in terms of the syntax for debugger display. And then some of the documentation on the new snapshot debugger that I showed you, debugging the cloud, is visible right there. At any rate, that's all I have. If you have any questions, feel free to come up. And I do have to